Hi, in this video I'm going to do a bunch of problems on statistical inference related to means and proportions especially to help my students in my introductory stats class, officially called Statistical Analysis at Bethel University in St. Paul, Minnesota, to study for their, well in this case it's going to be their exam 2 here in fall of 2017. Some semesters I have 3 midterm exams and it would be exam 3 in those semesters. So I've got old exam problems here. I want to focus on the problems that are more related to inference, of which this first one is not, or this second one. But the third problem is a problem about inference in this old exam. And so we will do it. And what I want you to do is I want you to, as you watch this video, to focus on maybe pausing the video periodically when you look at these problems and trying to think through them on your own, and then restart the video, see what I say. And I'm going to focus on how do you decide what kind of formulas to use, what kinds of formulas for confidence intervals, and what kinds of formulas for test statistics when you're doing hypothesis testing. Again, mostly for means and proportions, sometimes one sample, sometimes 2 samples. I think if we have time, we're going to do a chi-squared example at the end as well. If this video is not getting too long already, I will try to go as fast as I can to make the video as short as possible. All right, here we go. So let's start by, in this problem, reading it, and it says, assume you keep track of your golfing scores for your entire adult life and they happen to have a normal distribution. A random sample of 5 of your golfing scores are right here. The goal here, look for words like find a 90% confidence interval for your true mean score mu over your whole adult life. Note you'll need your calculator to find x bar and s, the sample standard deviation. That was a remark that I gave the people on this old exam. I didn't have to do that. That's something you should be able to do even if I didn't note that. Report your mean accurate to 1 place after the decimal, and report your margin of error or your endpoints accurate to 2 places after the decimal. Technically speaking, they probably should have the same number of places after the decimal, but I kind of like having 2 places, 1 extra place for the margin of error. State the value of df, the degrees of freedom, if it is relevant, and don't state it if it's not relevant. All right, so what kinds of key things do you look for? You want to look for the fact that you're talking about a mean. So this is a problem about a mean instead of a proportion. So there is a key word to look for and a key symbol, mu. You also have these symbols, x bar and s. And you notice, well, this is talking about 1 sample. So this is a 1 sample problem about finding a confidence interval to estimate a population mean, a single population mean. When you realize that's the case, there are 2 approaches that I talk about in my classes. Either you know the population standard deviation sigma, lowercase sigma, or you don't. We do not. You don't see a sigma here anywhere. In fact, for extra emphasis, I say find the sample standard deviation. So this is supposed to tell you, alert you to the fact that we should use a t statistic here, a t distribution rather than z. T being the student's t distribution, z being the standard normal distribution. We want to use a t distribution here instead of z. And the degrees of freedom will be relevant. df will be n-1 in this context. N is 5, so this is going to be 4. We're going to use 4 degrees of freedom. By the way, when we calculate p-values for these kinds of tests, I'll use both the table and a calculator to illustrate the use of both of those things. Probably with the confidence interval, we'll just use the table though. All right, so that's the case. So first of all, the point estimate is x bar plus or minus some margin of error. This is going to be your general form of the confidence interval. X bar plus or minus the margin of error in this context is going to be t star, a special value of t. Our book uses t star. Some other books use t with a subscript to emphasize the confidence level. But here, this is just emphasizing this is a special number that we get from the table, times the standard error for x bar. And the formula for that standard error is going to be s over square root of n. So once we calculate these numbers, we will be able to calculate the confidence interval. I did put the data into my calculator ahead of time to save some time here. Got a TI-84 here. If I go to stat mode and edit, you see in list 1 the golfing data, 78, 91, 86, 101, and 88. Okay, so that's in list 1, and it is double check that it matches those numbers. So now I want to calculate my statistics for that list. Go to Stat, go over to calculate. One variable stats, that's what we need. List 1, calculate. X bar is 88.8. That light is a bit bothersome here, sorry about that. Plus or minus, let's skip writing t star for the moment. S, use the sample standard deviation. Do not use the population standard deviation if you pretended these data were from a population. Use S. We are trying to estimate a population standard deviation with S. And let's see, how far should I round it? I'll go out one more place here. 8.34865 divided by square root of n is 5. All right, what is t star going to be? I'll go ahead and use a table, since I'll use tables for confidence intervals exclusively here. Here's the t distribution table. We have 4 degrees of freedom, so we want to look at the 4 degrees of freedom line. The confidence level for this table is down at the bottom. We are after, what is it, a 90% confidence interval? Yes, it is. So we look on this column for 4 degrees of freedom. And that will put us right here. 2.132 is the t star multiplier for such a situation. 2.132. All right, so now let's just use the calculator, get the answer. 8.34865 divide by square root of 5. The standard error for x bar, which is an approximation for the standard deviation of its sampling distribution, is about 3.7336. Multiply that by 2.132. Get a margin of error of about 7.69, and that would be rounded to 2 places after the decimal. So we could write our answer as 88.8 plus or minus 7.96. That would be plus or minus notation that emphasizes the midpoint of the interval at 88.8 and also emphasizes the distance to either endpoint, 7.96. And I'm fine with you leaving your answer this way, but you should, if I asked you, be able to find the endpoints as well. And so we'd do 88.8 minus 7.96 is 80.84, and 88.8 plus 7.96 is 96.76. We use parentheses to emphasize that we don't include the endpoints in this interval, but that's not a real big deal. I really could even use square brackets to emphasize to include the endpoints, but it's not really a big deal either way, whether you include them or not. Either answer is okay, and you should be able to derive one answer from the other if necessary. It's also good to briefly talk about what it means. It means we are pretty sure, 90% sure, that our true mean score, mu, over our entire adult life is in this interval somewhere. It's between 80.84 and 96.76. It's within about 8 of 88.8. Okay, that's what this is telling us. We're pretty confident that our true mean score, mu, for our entire adult life is in this interval somewhere. All right, so that's the first problem. Here is the second problem. On inference, a simple random sample of 4,000 adults, kind of a big sample, is asked what profession they would prefer their spouse to have. The choice receiving the highest percent, 905 of the responses, was doctors, nurses, and other healthcare professionals. Finding another confidence interval, 95%, to estimate the, okay, keywords here, true population proportion. This is a proportion problem of all adults in the U.S. who preferred that their spouse have one of these professions. State the value of DF if it is relevant. Well, the way we're approaching these things, we use the Z statistic for proportions. DF is not going to be relevant. You know that right off the bat. DF is not relevant. You wouldn't have to write that down, but you could. I guess I will for emphasis. DF is not relevant. All right. We are focused on proportions and a confidence interval. So proportions, what's the symbol for proportions? It's not a mean, it's not an x bar or a mu. It's a p for the population proportion and a p hat for the sample proportion, and the confidence interval formula is p hat plus or minus z star, special value of z, times the standard error for p hat, which is an approximation for the standard deviation of the sampling distribution of p hat. The formula for that standard error is the square root of p hat times 1 minus p hat divided by n. Okay, we are looking at one sample here. It's not a two-sample problem. What is p hat? It's not 905, it's not 4,000, it's the ratio 905 divided by 4,000. P hat is 905 divided by 4,000. 905 divided by 4,000, about 0.22625. Actually, that's that exactly, 0.22625. Z star for 95% confidence. Probably done that one so much that you might remember it. It's 1.96. It can be found from the same table in the textbook that I use at the very bottom here. 95%, there's a Z star line, 1.960. Okay, that's one of the more common ones to use. Again, that's a special number. That's the multiplier times the standard error to get the margin of error. This could be called M if you like. And it is one of the more common ones to use with 95% confidence is one of the most common confidence levels too. All right, let's go ahead and calculate the standard error and then multiply it by Z star and then include the 0.22625 in there. So I have p hat in here. It's an estimate, a point estimate for p, the unknown population proportion. I can do a square root right off the bat of this previous answer, 0.22625, times 1 minus the previous answer, divided by n. N is 4,000. Looks like this square root is about 0.0066. You could, if you're afraid you might make a mistake with the calculator, doing it the way I did, you could calculate it piece by piece and write down intermediate answers. And that way also, if you make a mistake, I can see where your mistake is more easily and give you more partial credit. But I'm going to trust that I've done it right here. I suppose in this video I'm trusting that I've done everything right, and I could make a mistake somewhere. Hopefully I will catch any mistakes that I made. Multiply this times 1.96. I've already taken the square root. So it looks like the margin of error is 0.01297 approximately. I didn't say how far to round things. I am okay typically to rounding things to what you might say is a reasonable amount. What is a reasonable amount here? Oh, I guess I'd say even 0.23 is reasonable for p hat. I'll do 0.226. And again, technically speaking, you should round the margin of error to the same number of decimal places, but I kind of like bucking the technical thing you should do and including one more decimal place, 0.012966. That'll round to 0.0130 actually. Okay, make sure you understand why. It's because of that extra 6 there. And then, so that's the plus or minus notation for the confidence interval, and then go ahead and find the endpoints if you like. 0.226 minus 0.013 will be what? 0.213. And then put an extra 0. Well, okay, we could put an extra 0 there if we like. And then 0.226 plus 0.0130 will be 0.2390. Hopefully I didn't make a mistake with my arithmetic either. That would be really embarrassing. Just double checking things. Yeah, okay. So that's the answer in either form. What does it mean? It means we're 95% confident, pretty sure, that the true population proportion, of adults who prefer that their spouse be in the healthcare industry is in this interval somewhere based on this simple random sample of size 4,000. Okay, we're pretty sure it's the true proportion somewhere between 21.3% and 23.9%. And that's another thing about proportions is you can write your answers as percentages. You can write it like that. All right, but again, we look for keywords. This problem is kind of long. Actually, it's kind of a funny thing in math. Oftentimes longer problems are easier. Partially, so this is longer because I was partially telling these students exactly what to do. I could have given them less information and they'd have to figure out what to do on their own. I'm not guaranteeing I'll do that for you or not. But let's just go ahead and do this problem. So we have a survey of study habits and attitudes, measuring students' attitudes in school. Scores range from 0 to 200. Oh, here's a keyword. The mean score of U.S. college students is about 115. Population standard deviation sigma equals 30. That sets off alarm bells in my head. We know the population standard deviation. We're going to be able to use Z instead of T. The teacher suspects that older students have better attitudes, and because of that performs this test, this right-tailed test. Now, I told them what to do here. It's possible I wouldn't tell you what kind of test to do, and you would want to focus on the fact that the teacher suspects older students do better. So that would mean they have higher scores based on this survey, and so that would mean you'd want to do a right-tailed test. The alternative hypothesis would have a greater than sign. Okay? So again, I told them that, but you should be able to do it without me telling you. Mu is the true mean score for all students over 30 years of age. I guess, yeah, we are focused on older students here. That's the population. She takes a random sample of size 16 from the population of students over 30 years of age, finds that the sample mean is indeed bigger than 115. It's 129.4. So it's bigger than 115, but that's not the issue. The issue is that far enough away from the null value to reject the null hypothesis. Is it statistically significant evidence? Can't be just a little bit far away. It's got to be a lot far away based on a given sample size. You know, the game from here on out to find the p-value, at least, is to decide, is this x bar far enough away from the null value based on a sample of size 16 to reject the null, to be statistically significant evidence against the null. By the way, we, in our book, use equalities for the null hypothesis, but some books, you should know, use less than or equal to's. And that's technically the better way to go, but just to keep things simple, we put an equal sign in here. You should know how to find the p-value of a test. Now, I told them the p-value is this probability, but you should be able to know that without me telling you. The p-value of a test, listen carefully, maybe write it down, is the probability of observing sample data, getting a test statistic, a Z, as extreme or more extreme as what you actually observe when you assume the null hypothesis is true, where as extreme or more extreme is with respect to the direction of the alternative, greater than, less than, or two-tailed. All right, so that is this probability, because we got a sample mean of 129.4, so as extreme or more extreme means x bar is bigger than or equal to 129.4. Find the probability of that happening when you assume the null hypothesis is true. Given, the vertical line means given that, mu equals 115. That's going to be the p-value. All right? Let's go ahead and do that. We can answer parts B and C pretty quickly. Go ahead and standardize, convert to z-score. You could conceivably plug this into your calculator right away, but I want you to be able to convert to z-scores as well if I asked you to, so you should be able to write it with this notation. It's going to be the probability that z, I get z by standardizing the x bar, is greater than or equal to what I get when I standardize 129.4. I'm not going to bother with the conditional probability notation. Still, I am technically assuming mu is 115. The key thing to put here is based on the fact that by the central limit theorem, the sampling distribution of x bar, at least when n is large, is that large enough? Well, maybe borderline, but we'll go ahead and assume it anyway. That x bar is approximately normal with mean mu and standard deviation sigma over square root of n. That's the central limit theorem, CLT, central limit theorem. So that's what justifies converting to z here by subtracting the assumed mean of 115 and dividing not by 30. That's a common mistake to just divide by sigma. Divide by sigma over square root of n. 30 over square root of 16. Make sure you don't forget the square root of 16 there. So that's the same as the probability that z will be greater than or equal to, this will be 14.4. Square root of 16 is 4. 30 divided by 4 would be 7.5. Hoping I don't make mistakes. All right, 14.4 divided by 7.5 is 1.92. So this is the probability that z is greater than or equal to 1.92. So if we use the table to find this, based on how this table is constructed, this table gives you areas to the left of different z values. If z is 1.92, we want the area to the right of it. We need to take 1 minus this number, 1 minus 0.9726. 9726, again, because this is a greater than or equal to, we're finding an area to the right of positive 1.92. It's going to be a fairly small area. According to this table, we'd use 1.92, we'd take this number and do 1 minus that. Technically, by symmetry, we could also take the opposite side of the table with negative z values, go to negative 1.92, and the answer would be 0.0274. By symmetry, we could technically just write that down. That will be the p-value here. Let me just show you how to do this also with the TI-84. So we are in a situation where we are doing a test that is a z-test, a one-sample z-test. We don't have data. We don't have the original data here. We instead have statistics. We've got x bar, for example, and we've got sigma. The null value is 115. That goes right here. Sigma is 30. X bar is 129.4. N is 16. And we are doing a right-tailed test. Calculate that. We get a p-value of 0.02742888, which does round to 0.0274. Okay, that is the p-value for this test. Part B. Should the null hypothesis be rejected, make a decision based on a level of significance of 5%. And so the rule there is the p-value less than alpha, the level of significance? The answer is yes, it is. 2.74% is less than 5%. So the answer is yes, reject the null. I didn't ask for more commentary, but you should be able to give more commentary. We have statistically significant evidence. Statistically, hopefully I spell correctly, significant evidence against the null hypothesis. And if you want to be extra picky about how you say things, you could say at the 5% level of significance. What the calculation is really telling us is if the null is true, if mu really is 115, the chance of seeing this x bar or greater is pretty small, less than a 5% chance. Therefore, we think the null is probably false, and we reject it. The p-value is not the probability that the null is true, though, okay? Nobody can calculate the probability that the null is true. It's the probability of observing a test statistic, an x bar and a z, as extreme or more extreme as what we actually observe when we assume the null is true. So again, when that's false, that means we think, okay, the null is probably, when that's low, we think the null is probably false, so we reject it. That is the logic, convoluted as it sounds. That's the way it goes. I could have also asked, what does it mean? Interpret the meaning of rejecting the null here. It means we think this is false. We think that students over 30 do have higher motivation and attitude levels and study habits. Okay, that would be the practical meaning of it. To what type of error are you now subject to? So this was part B. Part C, since we rejected the null when it could be true, that's a type 1 error that we are possibly making. We are subject to a type 1 error that, if there's an error that we're making, it would be a type 1 error. We don't know if we're making a type 1 error or not for sure because we don't know the true population mean. But if there is an error, it's rejecting the null when it's true. It's like convicting an innocent person. All right, on to the next problem here. I know this is getting long, but I think it's definitely worth going through all this. Okay, this is kind of a hard problem for people typically. It's a problem about power and the probability of a type 2 error. It's a little bit strange. We're pretending we know the population standard deviation, sigma, to be 2.5. Actually, you know, the assumption of knowing the population standard deviation is quite unrealistic. You know, if you don't know the population mean, mu, why would you know the population standard deviation, sigma? Though sometimes, to keep things easy, you go ahead and assume you know it anyway, if it's hopefully close enough. For a sample size of n equals 25, it can be shown that the null hypothesis for this right-tailed test can be rejected at the 10% level of significance if x bar is bigger than or equal to 5.641. Okay, what does that mean? It means that if you draw the sampling distribution for x bar, assuming mu truly is 5, this sampling distribution is going to be centered at 5, and the area under this to the right of 5.641 is going to be 10%. That's going to be the level of significance alpha 0.10. That's what this is telling us. This is not something you would know typically ahead of time. In more practical situations, if you were trying to calculate what we're calculating here, you would know alpha ahead of time. You would decide on alpha to be 10% or 5% or whatever, and you would calculate the rejection region. This is the region for rejecting the null. If x bar is bigger than or equal to 5.641, we are going to reject the null. It's in this region, for these values of x bars, that the p-value will be less than 10%. Although at the boundary, it probably would be equal to 10%. What's the goal? Find the power of the test to correctly reject the null when we assume that it's false, and we also assume mu truly is 6 instead of 5. Find the corresponding probability of a type 2 error in the same situation, assuming mu is 6. So that's where you fail to reject the null when you should have because it's false. That's like failing to convict a guilty person. And part C, find the probability of a type 1 error. And a little hint here, this last one's supposed to be easy. There's no calculations you even need to do for it. You might want to think about that before I come back to it later. All right, so part A, the power. It's the probability of doing something right, having power to do something right, correctly rejecting the null when it's false. So it should be rejected. As a prosecuting attorney, it's your probability of correctly convicting somebody who is guilty. So rejecting the null means x bar is bigger than or equal to 5.641. This is really a conditional probability. I'm assuming mu is 6. Assuming, given that mu is 6. That would be an alternative value of mu. It fits the alternative hypothesis. In this situation, we technically should reject the null. Now you might wonder, well, is mu really 6? To tell you the truth, nobody knows. Mu could be 6, it could be 7, it could be 5, it could be 6.2, it could be 6.34652. You know, it could be lots of different things here. We don't really know what it is. So we're doing these calculations in a hypothetical, essentially. But it's an important kind of hypothetical because it helps us decide, do we have enough power to proceed with this test? And if we didn't have enough power, we'd probably want to increase the sample size. It would be one remedy for that. How do you decide on mu equals 6? Well, here you're just told let mu equal 6, but in real life you want to pick the minimum value in the alternative region here where mu is bigger than 5. That for a right-tailed test at least would be important to detect. You know, if mu really is 5.2, you know, that's pretty close to 5. Maybe it's not a big deal to go ahead and assume the null is true in that situation. But you'd want to be able to detect it if mu is 6 or bigger, for example. So you do the power calculation based on that minimal value that you'd like to be able to detect. Go ahead and convert to a z-score, and as before, I will not bother writing a conditional probability anymore. We need to subtract the assumed value of mu, in this case 6, not 5. I'm not assuming the null is true, I'm assuming this alternative value is true. divided by sigma over square root of n, just like that other problem a few minutes ago. What's really going on here is we're assuming mu is 6, so back up in this picture, if we draw a normal curve centered at 6 with the same amount of spread, say about like this, we're really trying to calculate the area under this curve to the right of 5.641, which is going to be bigger. It's going to be a relatively high power, which is good. All right, go ahead and now simplify a bit. So we got a what? A negative 0.359 up top. 2.5 divided by square root of 25 is 2.5 divided by 5 is 0.5. So negative 0.359 divided by 0.5 gives approximately negative 0.72. The area is going to be bigger than 0.5. To the right of negative 0.72. Let's see here, where'd my table go? Here it is. So again, this kind of table gives you areas to the left. We want an area to the right. So if we use it based on z equals negative 0.72, we're going to need to do 1 minus negative 0.72. We'll take 1 minus 0.2358. 1 minus 0.2358. You could do that without doing 1 minus. By symmetry, the area to the right of negative 0.72, analogous to this area up here, would be the same as the area to the left of positive 0.72. 0.7642 right there. And that's what the subtraction does give you, 0.7642. That is the power of the test here. A typical kind of standard power that people like is 80% or higher. This is pretty close. But in real life, if you wanted to get it to more than 80%, you'd want to increase the sample size. If detecting the value of 6 was truly important to you, increase the sample size. It'll make the sampling distributions skinnier and will make the power higher here. All right, the probability of a type 2 error, where you fail to reject the null when you should have, you failed to convict that guilty person, is the probability that you do not reject x bar is less than 5.641, given that mu is 6. And that's 1 minus the probability that x bar is bigger than or equal to 5.641. It's 1 minus the power when you're assuming mu is 6, which is still what we're assuming. 1 minus 0.7642, and that is 0.2358. How about the probability of a type 1 error? There's no calculations you need to do. It's the same as the level of significance alpha. See the probability of a type 1 error. I should probably put the word error in here. Is alpha is 10%. When you decide on alpha ahead of time, you are deciding on what the probability of a type 1 error is going to be. Okay, and that's, you know, if you're making a type 1 error results in something bad happening, like people dying or something, more than making a type 2 error would, then you'd want alpha to be really, really small, like 1% or even smaller. So that could increase the probability of a type 2 error. All right, what's next? Oh, I guess same page here. You know what? I think for the sake of time, I'm going to skip this one. Though I would like to talk about the Two Towers, Lord of the Rings. You can tell how old this problem is. Currently, I'm making this video in 2017, but this problem goes way back to the year 2003. And by the way, these are made-up prices. You would do a t-test for a mean, because we are after approximating the mean price. That would be the population mean, but we've already done a problem like this. A one-sample t confidence level interval. All right, how about this one? All right, long problem. Does that mean it's easy? Well, not necessarily. People do seem to have trouble with this one when I've given it, but I'm giving you everything you need. So we've got an agriculture problem, sample surveys. We've got 2 different months here, July and August. Independent samples, notice the S. There's 2 samples here. In these 2 months, here are the summary statistics about prices in dollars per bushel for July and August. two samples, so we've got two sample sizes, N1 and N2. We've got two sample means, notice the bars, X1 bar and X2 bar. Two sample standard deviations, S1 and S2. This should be causing you to realize, okay, this is a problem about means with two samples. We need the t-distribution. So it's, well, in the book I use, it's a chapter 7 problem. Question is asked here, can we conclude that the national average price in July, mu1, that's mu1, sorry, I kind of wrote over that, and the national average price in August, mu2, are not the same? So evidently we're going to do a hypothesis test. Answer this question in two ways with the correct degrees of freedom. I didn't have to say with the correct degrees of freedom, and you would need to be able to decide the degrees of freedom for yourself. Calculate a 95% confidence interval for estimating the difference, mu1 minus mu2. Calculate the two-sample t-statistic. Use table D, which is the t-table, to compute the range of possibilities for the p-value. We'll also use the calculator and get a more precise p-value. This is our test. It is a two-tailed test. Notice that. mu1 is not equal to mu2 in the alternative hypothesis. What do your answers say about whether mu1 and mu2 are the same at the 5% level significance? And to what type of error are you subject to? All right, so we're doing the confidence interval first. We're trying to estimate mu1 minus mu2. Why? Well, if mu1 minus mu2 were 0, if the population means differences was 0, they would be equal. If this difference is positive, that would be evidence that mu1 is bigger than mu2. Or if I said that wrong. If we end up getting evidence that x1 bar is bigger than x2 bar, which it is, that would be some evidence that mu1 is bigger than mu2. x1 bar minus x2 bar would be our point estimate, and that would be positive. And the flip side if it were negative. The point estimate here is x1 bar minus x2 bar, and that's a logical point estimate for mu1 minus mu2. That's your parameter. These are your statistics. Plus or minus a margin of error. We're using a t-distribution, so t star is the symbol for the special value of t that we need, based on a certain number of degrees of freedom. Again, other books use subscripts to emphasize what the confidence level is, but our book keeps it simple and just says the special value of t, times the standard error for x1 bar minus x2 bar. Might want to put parentheses around this for extra emphasis. This standard error is the square root of s1 squared over n1 plus s2 squared over n2. That's the standard error for this, meaning it's an approximation for the standard deviation of the sampling distribution of x1 bar minus x2 bar, which does look normal. Okay? So now it really is a matter of just plugging numbers in. We can do some of this in our heads here. And we also have to get the right degrees of freedom here as well. 7.72 is x1 bar, minus 7.54. That will be in dollars 0.18, 18 cents. Plus or minus t star. Okay, what are the degrees of freedom here? I didn't ask for whether it's relevant or not, but it is. I always take what you might call the conservative approach for the DF in this situation, which is the simplest approach to take. You just take the smaller of n1 minus 1 and n2 minus 1. 32 minus 1 is 31. 27 minus 1 is 26. Take DF to be 26. There technically are other DFs that are more accurate that you can get with technology like the calculator or something called the Smith-Satterthwaite formula, which is really complicated. But this is a simpler approach. It's also more conservative. The t-star is going to be bigger than the more accurate approaches, giving us a bigger margin of error, a bigger confidence interval, and bigger p-values for tests. And that's good enough. It's better to be conservative in this approach rather than being risky. So based on 26 degrees of freedom, if we use the table, DF is this column here. 26 degrees of freedom is right down there. And we are after what confidence level? We are after a 95% confidence level. 95 up to 26, 2.056 is the value of t star. 2.056 times the square root. I'll just go ahead and write the numbers. 0.25 squared, there's the 0.25 up there. That's S1. Divided by N1, which is 32. S2 is 0.31. 0.31 squared divided by N2, which is 27. Again, if you want to get the most partial credit possible, you might want to show lots of intermediate steps in this calculation, but I will just go ahead and calculate the square root right away here, looking right there, and hope that I don't make a mistake. Square root of, okay, 0.25 squared divided by, oops, got a tab over there, divide by 32 plus 0.31 squared divide by 27. The calculator should do things correctly as far as order of operations go. It's real important that you know the order of operations. Do the 0.25 squared over 32 and the 0.31 squared over 27 first before you add. And then take the square root at the end, but the calculator should know to do this correctly. Looks like the standard error here is about 0.074245. Multiply it times 2.056. Get about 0.1526. So our confidence interval is $0.18 plus or minus. To the nearest cent, it would be 0.15 cents. I like going one more decimal, even though it's not practical with cents. 0.153. Really, it should be to the nearest cent, 15 cents here. In interval notation, you can put the dollar sign outside the parentheses if you like, or inside, it doesn't matter. It would really be a 0.03 here. You could 0.027 and then a 0.333. So about between 3 cents and 33 cents is the confidence interval, the 95% confidence interval to estimate mu1 minus mu2. That says, since it doesn't include any negative numbers, that we are pretty confident that mu1 is bigger than mu2, that the difference here is positive. That is evidence, statistically significant evidence, really at the 5% level based on a 95% confidence interval for a two-tailed test, that we have strong evidence against the null. Okay, we would reject the null. Does B confirm this based on doing the hypothesis test in the ordinary way? We need to calculate a t statistic. That will be x1 bar minus x2 bar over the standard error for x1 bar minus x2 bar. We have these numbers already. Actually, the units are going to cancel anyway, so I won't bother putting them. 0.18 for the difference up there, and the standard error here was 0.074245. All right, do that quotient, 0.18 divide by 0.074245. Gives you a t-stat of 2.424. Again, 26 degrees of freedom. So what does that mean? Go back to the same table, 26 degrees of freedom. We're looking for two numbers that bracket 2.424 on the 26 degree of freedom line. 26 degrees of freedom, 2.424 is bracketed by these two numbers, 2.162 and 2.479. If I now go up to the top, the one-tailed probability, the one-tailed p-value would be between these two, but we are doing a two-tailed test, so our p-value is between taking these two numbers and doubling them. It's between 2 and 4%. So our p-value is between 2 times 0.01 and 2 times 0.02. It's between 2% and 4%. Make sure you write the inequalities the right direction. I know all across the table, the top of this table, they're going from greatest to least. But when you write it this way, go from least to greatest and use less than signs, okay? It's a common mistake. People write the inequalities the wrong direction, and technically I can take points off for that, so don't do that. All right? Anyway, it's a small p-value, less than 5%. We are making our decision based on a 5% level of significance, so we do reject the null. We have strong evidence at the 5% level that the true mean prices for the wheat in July and August are different. Okay? In fact, the one-tailed p-value would be even smaller for a right-tailed test. And we have you could say, statistically significant evidence that mu1 is bigger than mu2. All right, we're rejecting the null. I should say that here, reject the null. You could also write it seems that mu1 is different than mu2. These prices are different based on these samples. Since we rejected the null, we're subject to a type 1 error. We rejected the null, but it could be true. Let me show you the calculator usage here as well, but before I do that, and before we go on, I should emphasize that this table has limitations. Once you get to 30 degrees of freedom, then it skips by 10, and then you get to 60, it skips by 20, and then by 900, and then there's nothing after 1,000. So what happens if your n is like 73? There's no df equals 72 here. What do? Well, you could round to the closest one, 80. Or if you want to play conservative, you can always round down. And that's what I suggest, is rounding down to 60. All right, let's also double check this with the calculator. We'll get a more precise p-value with the calculator. Go to stat, tests. We are doing a 2-sample t-test. We're doing it based on statistics, these numbers up here, not data. X1 bar was 7.72, S1 was 0.25, N1 was 32. Hoping you wrote those numbers down. X2 bar was 7.54, S2 was 0.31, and N2 was 27. We're doing a two-tailed test. We are not pooling. We're not assuming the population standard deviations are the same. Calculate the p-value. It's giving us a p-value of 0.019. So the calculator is giving us a p-value of 0.019, which is not the same as the p-value we got. Why not? Well, remember, because we used the conservative approach. We took df to be the smaller of n1 minus 1 and n2 minus 1. It's not as accurate as it could be, and it results in bigger confidence intervals and bigger p-values. Our p-value, according to that approach, is between 2 and 4%, which is technically a little less accurate than this p-value that the calculator is using, is based on this degrees of freedom. But it's going to be fine. It's good enough to see that we should reject the null hypothesis here. All right, so what do we have left? We've got 2 more problems left here. Glad you're hanging with me. I'll try to go as quick as I can. There's one more that's a mean or proportion problem, and then there's a chi-square problem. What do we have here? We've got a random sample of 321. It's reported that 43% participated in community service or volunteer work. That sets off alarm bells in my mind right away. Okay, percentages are the same as proportions. And in fact, I see again on part A, we're finding a confidence interval to estimate P, the true proportion of all first-year college students who participated in community service or volunteer work. So we are talking about a proportion problem. We will use Z. And you look it over, it does seem to be a 1-sample thing instead of 2 samples. The head of the U.S. Department of Education thinks the true proportion of all college students first year who participate in community service or volunteer work is 38%. But Bethel University, that's where I work, their director of service learning thinks that it's higher. Based on a sample size, again, of 321, find the p-value for this test right here. The null hypothesis being that p, the population proportion, is 0.38, versus the alternative that p is bigger than 0.38. Who do you think is right based on the head of the department, the head of the U.S. Department of Education or Bethel's director of service learning, and make your decision based on a 5% level of significance? So this is a proportion problem. Hypothesis test, we are going to use a Z statistic. It's going to be, the Z statistic is going to be p hat that we get from the sample, which is 0.43, minus the null hypothesis value, which is 0.38, divided by the standard error for p hat, the approximation to the standard deviation of its sampling distribution, though this is a little tricky here. Because we are assuming the null hypothesis is true, we calculate the standard deviation or standard error not with p hat, but with p0 instead, with 0.38. That's p0, the null value. So we put 0.38 times 0.62 divided by n, which is 321. Okay, we are assuming the null is true when we do the test, so we use the null value rather than the p-hat value of 0.43 here and here. P0 times 1 minus P0 divided by n, take the square root. I was assuming you knew that formula. All right, so we've got then on the bottom here, again I'll do it all at once, square root 0.38 times 0.62 divided by 321 is 0.0271 approximately. Do 0.05 divide by that. Gives you a z-statistic that's about 1.85. This is a right-tailed test, so the p-value is the probability of getting a test statistic that extreme or more extreme when you assume the null is true, which is z greater than or equal to 1.85 because it's a right-tailed test. By the way, it really doesn't matter whether you put a greater than or equal to or a strict greater than here because it's a continuous distribution. So once again, we use the table. I think I'll just use the table this time. We're after an area to the right of 1.85. The table gives you areas to the left, this table at least. 1.85, the area to the left is 0.9678. So this is 1 minus 0.9678, which will be 0.0322. Pretty small p-value, less than 5%. We reject the null. We think Bethel's director of service learning is the correct one. Okay, we have statistically significant evidence at the 5% level that against the null hypothesis here. So we reject it. And we would be subject to a type 1 error. All right, last problem. This is a chi-square problem, and when I give chi-square problems with calculations, I typically fill in the tables to a large extent and the chi-square statistic, and you just need to finish things. So what do we have here? We have two different large sections of a stats class. The University of Minnesota had data shown below on passes and fails. Is there statistically significant evidence for a difference in the passing failing rates between the two sections, assuming these are samples from a larger population, random samples? Do a chi-square test to answer this question by filling in the tables and the partial formulas below. Here's the actual table and the partially filled in expected table. It's not completely filled in. We need to figure out what goes there. Then we need to figure out what goes here, here, and here, and then there's more to answer after that. So you need formulas you need to know how to do these things. The formula, so these are the actual numbers. So for example, in section 1, 55 out of 70 passed, 15 out of 70 failed. Section 2, they did better, 66 out of 69 passed, 3 out of 69 failed. So that's, it seems that section 2 did better than section 1, but these are supposed to be samples from a larger population. Is it statistically significant evidence that the section number affected the pass-fail rate? That's what we're really after here. Well, the way to figure out what number goes there, the trick is you multiply for that row and that column, the row total and the column total, and then you divide by the overall total. That's the method. In my lectures on this subject, I do talk about the logic behind that. It is based on assuming that the null hypothesis is true, that these sections numbers don't affect the pass-fail rates. But the method, again, is to multiply 18 times 69 divided by 139 and get 8.93525. Calculation of the chi-square stat, you take in the numerator, you take for each of these 4 spots, you take the actual number. In this case, for this spot, it's 3, minus the corresponding expected number, based on assuming the null is true. Square that, and then divide by the expected number. So we would take 3 minus this number, square that, divide by 8.93525. This number simplifies to about 3.9425. I will write that here, 3.9425. Now we just need to add up those numbers. 3.8862 plus, going backwards, 0.5865 plus 0.5781. The value of the chi-square stat is about 8.9933. Okay. DF is always, for the main body of the table, the number of rows minus 1 times the number of columns minus 1. This is a 2 by 2 table, 2 rows, 2 columns. R and C are both 2. 2 minus 1 is 1. We get 1 times 1 is the degrees of freedom. We need to now use the chi-square table. If we're using the table, based on 1 degree of freedom, our test statistic value was 8.9933. On the 1 degree of freedom line, that is bracketed by these two numbers. So the p-value is between these two numbers. Okay, and we don't need to double these. It is technically a two-tailed test in a sense, but it's already taking that into account here. So the p-value is between 0.0025 and 0.005. Again, make sure you get them in the right order, smallest on the left, bigger on the right. Those bracket the p-value, and those are small p-values. This is less than alpha, 0.05, that's 0.5%, that's 5%. We do have statistically significant evidence against the null hypothesis that the section proportion of pass-fail rates are the same. We think they are different, and in fact, section 2 definitely looks to be better. All right, so that ends this long video about practicing problems about statistical inference that often gives students trouble on exams. So I hope you got a lot out of this to help you do well on your exam.